Okay, so first of all, thank you very much to the organizer to inviting me. It's a great pleasure to be here. It's an honor to celebrate Jakob's birthday for me. I mean, Jakob has been a great influence to our whole community, in particular certainly to my work on the Bose gas, since the time I was doing dynamics, and also now that I'm working on Bogoliubov theory. I mean, I think that all of these things started with this Lieb and Ingvason paper back in 1998. So thank you very much for that, for stimulating our work, and also thank you very much for your service, in particular for being director of the institute. When I grew up scientifically, we were having a lot of conferences in this place, and it was really nice to always be able to come here and learn new things and discuss with people. So thanks a lot. Okay, so today I would like to discuss some recent results that I obtained in collaboration with Moritz Brooks, Jakob Oldenburg and D, Aubin, who are all here, about the Wu correction term for the energy of a dilute Bose gas. In particular, I'm going to present an upper bound which captures the correct third order term in the expansion of the energy for dilute gases. Okay, so let me start. I mean, Jan-Philippe already defined most of the things. I will be quick, therefore. So I'm going to consider a system of bosons, so a Bose gas, n particles in a box with side length L, and I'm going to impose Dirichlet boundary condition, but this, of course, is not an important assumption. You can replace with different boundary condition in this big thermodynamic box. It does not make a difference. The Hamilton operator we are going to consider as this form here. The first term, of course, is the kinetic energy of the n particles, and then there is a two-body potential. We are summing over all pairs of particles with V of xi minus xj. We are going to assume later that V, for our result, is in L2. It's going to be radial, and it's going to be short range. For our upper bound, we are not going to assume positivity. Many results that Jan-Philippe talked about rely on positivity, on pointwise positivity of a potential. We only need some stability assumption of V, but that's just because it's only an upper bound, right? So that's clear that we don't absolutely need positivity. We are going to call A the scattering length of a potential V, and of course, as you already saw in the previous talk, this is a very important quantity. We are going to describe the energy of the system in terms of this scattering length A. So the scattering length is defined through the solution of the zero energy scattering equation, which I wrote here. This is an equation on the whole R3, and we impose the condition that F goes to 1 at infinity. And then if you assume that V is short range, so compact support, as soon as you are outside the support of the potential, well, you need F to look like 1 minus some constant divided by x, and this constant here is the scattering length of a potential. So the scattering length is sort of an effective range of a potential. If particles are far away from each other, they see each other as a hard sphere with radius A. Okay, good. So we are interested in the thermodynamic limit, which means we are going to let n and L, so the number of particles and the volume, to infinity, keeping the density fixed. That's the same limit that Jan-Philippe discussed in the first talk. And we are looking at the energy per unit volume, so the energy density. We take the ground state energy of the Hamiltonian on the previous slide, we divide by the volume, we take the limit, and we define this quantity E, which is a function of the density rho. And then, of course, we are interested in the behavior of this function E of rho for small rho, right? On a asymptotic expansion as rho goes to 0. But rho goes to 0, but right before we look at small rho, we let n and n go to infinity. So these are two different limits. First, you take the thermodynamic limits, and then you specialize on small density. And of course, as you already saw in the previous talk, this question was considered already in the 50s by the physics community, and there has been this Li Wang-Yang paper in 1957, and later in 1959 there was a paper of Wu, and there was also a paper of Hugenholz and Pines, if I remember correctly, maybe Savata, anyway, after the work of Li Wangyang, people started to worry about the next order correction, and Wu was the first one to predict that the next order term in the expansion for small rho has this form here. So you see that Li Wangyang here is rho to the 1/2. The Wu term is order rho times log rho, right? It is just a little bit bigger than order rho. And then there are lower order corrections, which are expected to be of order rho. You see, also the Wu term, like the Li Wangyang term, only depends on the potential through the scattering length A, right? This is the only thing that you see here, depending on the potential. There is no, does not depend on exactly what is the form of the potential. It only depends on the scattering length. So the expectation is that the next order term, which is of order rho, without the log, so a little bit smaller, because there is no log, that's not going to be universal anymore. That's going to depend also on other characteristic of the potential, and not only on the scattering length, right? Because at the next order, you can imagine that free body scattering starts to be important, while A only describes what happens when two particles scatter at each other. Okay, so now very briefly about the history in the mathematical physics community. We already heard most of it from Jan Philipp, but I have some more paper here to refer to so that the organizers don't complain. So the first rigorous result about this question about expansion for the energy at low density was the upper bound found by Dyson already in 1957. The matching lower bound was derived 40 years, more than 40 years later in this famous paper by Lieb and Ingvason, which sort of started all the work in our community about the Bose gas. Okay, so then we heard in the previous talk about the second order correction, so the Li Wangyang term. So upper bounds were given by Yao and Dean in 2009 for some sufficiently nice class of potential, and more recently in a joint work with Giulia Basti and with Serena Cenatiempo, we had, I think it's fair to say, an easier proof of the upper bound, which also extended to a more general class of potential. Still, we needed integrability. So I think that, if I remember correctly, we assume the potential to be in L2 or L3. So this still does not cover the case of a hard sphere, as already pointed out by Jan Philipp. The lower bounds for the Li Wangyang terms have been proven by Søren Fournet and Jan Philipp Soloway in two papers. The first one for integrable potential, and the second one extending also to potential with possibly hard sphere at the core. Okay, and then I mentioned also here recent extension also to positive temperature of these results here about the Li Wangyang energy. Positive temperature, but small temperature, right? So this was restricted to temperature which are smaller than order rho in this thermodynamic limit, and the lower bound was given by this paper here, Haberberger, Heinzel, Nams, Haringer, and Trier, and the upper bound I was also involved, and it is this paper here. So it's an extension of the formula to the Li Wangyang order to small positive temperature, if you want. Okay. So what I'm going to present here today is something about the next order, this Wu term here. And it is an upper bound for the Wu term. So that's a theorem which I said is together with Morris, Jacob, and Diane. So we assume the potential to be L2. Radial, as I said, we don't need the pointwise positivity. Some stability condition is enough, and we assume the support to be compact. Then we find an upper bound for the energy density in the ground state, which matches, you see, the Wu prediction up to error, which are of the order rho A cube, which is expected to be the optimal size of the error. Good. Now, in the rest of the talk, I would like to maybe try to give some idea about the proof. I mean, the proof is quite technical, but I think that I would like to try to convey some of the main idea. And the first idea that we use is this standard idea of localizing your system into smaller boxes, right? This allows us to study the problem of estimating the ground state energy, not in this large thermodynamical box, but in smaller boxes whose size is proportional to some inverse power of the density. So they're still large because the density is small, but they are large as rho to the minus gamma or something like that, not like the thermodynamic length L, which goes to infinity at the beginning. Okay? Now, maybe just some general remarks. See, localization is very important when you want to prove a lower bound. The reason why you need localization when you want to prove a lower bound is because you don't know how to prove Bose-Einstein condensation in this thermodynamical box. So you go to the small box, right, where you have spectral gaps. On the small box, you can prove condensation. You can get an estimate for the energy density in the small box, and that implies, if you have the right boundary condition, an energy estimate or an estimate on the energy density in the thermodynamics box by sort of additivity properties of the energy. Okay, so it's very important if you want to prove a lower bound because, simply because we don't know how to prove Bose-Einstein condensation in the big box. We don't have a lot of control on the state in the big box, right? For the upper bound, using localization is less fundamental, of course, because we don't need condensation, right? If you want to prove an upper bound, all you have to do is you have to construct a good trial state. And if you define your trial state yourself, you can define the trial state as exhibiting Bose-Einstein condensation. You don't have to prove that every state with the right energy or every candidate for the ground state exhibits Bose-Einstein condensation. Still, even if you don't have to prove Bose-Einstein condensation, using localization is sometimes useful, even if you want to prove an upper bound, because it's not so easy to control correlation among particles on very large length scales. So if you do it in the small box, it's a little bit easier than if you do it directly on the thermodynamical box. Okay, so what we do here, maybe I can draw a picture. So we start by the big box. This is a capital L. And instead of constructing a trial state on this big box, we divide it into smaller boxes, like that, right? And we construct a trial state only on the small box. And on the small box, we impose Dirichlet boundary condition, so that if you have a Dirichlet state here with a correct energy density, then you can just copy the same trial state in each one of these boxes, and you will find a trial state on the large thermodynamical box with a correct energy density, with the energy density which allows you to prove the estimate in the theorem. Okay? So you see the problem boils down in showing energy estimates, ground state energy estimates on the small box. So let's call this L. As I said, L is going to be some inverse power of the density. Still large because the density is small, but fixed, not depending on the capital L. Okay? Now, how do you prove an upper bound on the small box imposing Dirichlet boundary condition? Well, what you want to do is you want to take a box which is a little bit smaller, right? And then on the smaller box, you impose periodic boundary condition. So you look at the periodic problem in this smaller box, and then you impose a cutoff, right? Making sure that your state goes down and satisfy Dirichlet boundary condition in the slightly larger box, okay? Now, of course, this cutoff is going to affect your energy, right? So you want to make sure that the cutoff, the energy produced by the cutoff is smaller than the order of the energy that you want to resolve, okay? So the more precise estimate you want to get, the larger this box will have to be in order to make sure that the error caused by this cutoff here is not going to affect to this order the energy that you want to prove, okay? So this gives us a lower bound on how big this gamma can be. Okay, if you want to prove an upper bound to the Lee-Wang-Yang order, you will need gamma to be bigger than 1. If you want to prove a bound on the Wu scale, so you want to identify this term here, the error that you produce by localization should be even smaller than this term here, you will need gamma to be bigger than 3/2. Okay, so bigger than we had for Lee-Wang-Yang. So this is an additional difficulty if you want to go from Lee-Wang-Yang to the Wu term. Okay? Good. Now, if you reduce yourself to a small box, of course, you are giving a relationship between the size of the box, depending on the density, and the number of particles in the box, right? The number of particles should be like rho times the volume, rho times L cubed, so it's 1 minus 3 gamma. So you see, you induce a relationship between the number of particles in the system and the size of the system. It is convenient for us to rescale length so that this box here, this torus here, I should say, because it has periodic boundary condition, has size 1. If we divide all the length by 1, the size of the torus is going to be 1. But what you're going to see is that the potential is going to scale with a density or equivalently with the number of particles, n. Okay? So the problem for us boils down to understanding the ground state energy of this Hamilton operator here, where you see, now I switch from this exponent gamma to a new exponent which I call kappa. There is a direct relationship between the gamma and the kappa. I just want to parameterize the size of this box here, how it depends on rho. Okay, but when you we define the appropriate relationship between kappa and gamma, once you divide all the length by that number, so that we go down to the box of size 1, to this unit torus, the Hamiltonian will look like that, where the potential has a scattering length, which is now rescaled. You see, the scattering length of this guy here is n to the minus 1 plus kappa times the scattering length of the original potential v. Okay? So the problem boils down to understanding the ground state energy of this guy here on the unit torus, and there's assumption that gamma is large enough, translating the assumption that this parameter kappa is large enough. Okay? And if you do the computation, you find you will have to prove an estimate, an upper bound for the ground state of this guy for kappa larger than 4/7. Okay? This kappa equal to 4/7 corresponds to the gamma equal to 3/2 in that language. It's the same thing. Okay? Now, if you forget for a second about maybe I should have commented also on this formula here. This is just when you take the Wu formula that you have here, right? And you replace rho, which is now rho a cube, which is now n to the 3 kappa minus 2. If you use this notation here, you find this expression here for the energy. This is exactly the same as this one when you take the density to be the correct n-dependent function. Okay? Good. Now, if you forget for a second that we want to look at kappa bigger than 4/7, we can ask, well, what happens in the simplest possible case you can think of, what happens if you take kappa equal to 0? If you take kappa equal to 0, you recognize that the Hamiltonian that I wrote here, the potential is like n squared v of nx, and this is exactly the Gross-Pitayevsky scaling regime, right? This Gross-Pitayevsky scaling where the scattering length is of the order 1/n, and you are in a box of size 1, okay? Now, for the Gross-Pitayevsky case, so for kappa equal to 0, we have much more information, as already Ian Phillips said before. So the Li-Wang-Yang term was determined in this paper that I wrote with Chiara Boccato, Christian Bennek, and Serena Cenatempo. They're also all here, I think. Yes, I saw all of them. Hi, Chiara. In 2019, and this was the expansion of the ground state energy up to the Li-Wang-Yang order. So this sum here corresponds to this number 128 divided by 15 square root of pi that you see in the Li-Wang-Yang expression, right? In the thermodynamic limit, this sum becomes an integral, and if you perform the integral, you get this strange number. And more recently, in joint work with Cristina Caracci, Alessandro Giatti, and Ian Saint-Omer, we also were able to go to the next order, the Wu term, you see it here, okay? But this time not only as an upper bound. For this, in this regime, we have an upper and also a lower bound. So we really see the full emergence of this Wu term in the Gross-Pitayevsky regime, okay? And I think that Alessandro is going to talk about this result in his talk, maybe on Thursday, if you remember correctly. On Wednesday, sorry. Okay, good. Fine. So for the Gross-Pitayevsky regime, kappa equal to 0, we understand up to the Wu term, we understand everything. But the problem is we will not apply directly this result here because, as I pointed out in the previous slide, to go to the thermodynamic limit, to make sure that this localization error is small enough, we need kappa to be larger than 0, much larger than 0. We need kappa to be at least 4/7. Okay, so that's the challenge now, to understand how to prove this upper bound here when kappa is large enough. Good. So that was the first simplification of this kind of localization idea, which, as I said, you find pretty often in this business. The second, yes? That's just a technical. You're talking about this log n to the 1/2. This should be 1 over n. We were a little bit lazy, and I mean, the paper is already quite long, so we bounded some of error by log to the 1/2, which is smaller than log n over n, but this is expected to be 1 over n error here. Okay. So I was saying that the second simplification, we want to switch from a canonical picture where we fix the number of particles to some kind of grand canonical representation of the system. So we switch to the Fock space, where we take the direct sum of all possible number of particles, and our Hamiltonian in second quantized form assume this form, this expression here. Okay? So now you recognize the same creations and annihilations operator that we saw already in Jan-Philip's talk. You see the fact that the potential has scattering length of the order n to the -1 plus kappa translates into the Fourier transform of the decay only on momenta of order n to the 1 minus kappa. Okay, so that's what comes from the particular scaling that we are looking at. And in this grand canonical picture, what we need to do in order to prove the theorem that I mentioned before is to find a trial state in the Fock space, so not with a fixed number of particles, but making sure that the expected number of particles is at least n. We need some control on the variance of the number of particles to, well, this is used to translate the grand canonical result into a canonical result. Maybe it's not even needed, but I just wrote it here to be on the safe side. And then we need a bound on the energy. And of course, the bound of the energy needs to identify these three, the leading term, the Lagrangian term, and the Wu term up to error, which are of smaller order. Okay, so that's the goal. So the question is, how can we construct a trial state in the Fock space, so number of particles is not fixed anymore, satisfying this bound here with at least n particles. Good. And now the starting point of our analysis, of course, is again Bogoliubov theory. And Bogoliubov theory tells us how to, if you want, how to model the condensate, right? And that's where it's very useful and convenient to be on this Fock space without fixing the number of particles, because we can model the condensate through a coherent state which is generated by the Weil operator. And the algebra of the Weil operator is very easy and simple and nice, and that's why it's convenient to go to this Fock space representation. Okay, so this is the Weil operator I was referring to. This Weil operator generates a condensate with, in average, n0 particle in the state with 0 momentum, so just a constant. We are here in the box, in the unit torus lambda from, volume equal to 1, so the 0 momentum state is just a constant 1. Okay, and so this is what happens, thinking of including this coherent state into the definition of your trial state, right? Effectively, then the Weil operator is going to act on the Hamilton operator. You can think of it in terms of state, or you can think of it as unitary transformation of the Hamilton operator, and you know how the Weil operator acts. You just have to shift all A0 and A0 star creations and annihilations operator by a factor of square root of n, and that's what you find. So the usual expression, this is the constant contribution, then you have quadratic terms in the first and second lines, and then there is a cubic correction and a quartic correction here. Okay? So now the second step in Bogoliubov theory, right, is to conjugate with a Bogoliubov transformation. Now, for us, the Bogoliubov transformation has two goals. First of all, it acts on high momenta to renormalize the interaction. Okay? So when you take this transformation, this unity transformation here for p large enough, the effect of this guy is going to extract from the quartic, well, in this case only from the quartic term, new contribution to the quadratic and to the constant part of the Hamiltonian, which is essentially going to change some of these v hat terms into the scattering length, because at the end we want to generate this scattering length, right? You see, after the conjugation with the while operator, the constant term is proportional to the hat of 0, not to the scattering length. So here we need to correct this thing here, to renormalize this quantity here to find the right formula. And one step to do that is to conjugate with this thing here. So that's the action at high momenta. At low momenta, the effect of this guy here consists in diagonalizing the quadratic part of the Hamiltonian. So you see that here we have A star A terms, two of them, but we also have A star and A terms, which we don't like so much because we cannot compute the energy. And that goes back already to the original work of Bogolyubov. To get rid of this term here, you want to conjugate by something like that, which is going to reduce everything to a diagonal quadratic expression. Okay, so we have these two goals, and to achieve this goal, we have to choose these coefficients mu p, well, by this formula here. If we do this choice, roughly speaking, after conjugation with the Bogolyubov transformation, we find a new Hamilton operator. This is just the conjugation of the original operator, first with the while operator and then with the Bogolyubov transformation, which has essentially this form here. So the constant now is the Li-Wang-Yang energy. Then there is a quadratic part which is now diagonal and with this special dispersion law characterizing excitation of the condensate. And then there are corrections. There are the cubic parts, which I still have here, and the quartic part, which I call Vn. Okay? And sigma p, which appears somewhere here, that's just the sinh of mu p. It comes from the explicit action of this Bogolyubov transformation. Okay? Now, I should be to be more honest. So this is not exactly what you get. Okay? So first of all, you need at least to do a conjugation with some cubic part in order to get something like that. And second of all, well, we know how to do it rigorously only if kappa is equal to 0 or a little bit above 0. We certainly don't know how to do it rigorously for kappa bigger than 4/7. But we use this as a motivation of how we are going to choose the trial state. Okay? And since it's only a motivation, I can do whatever I want. Okay, so then we get something like that. And the second remark that I wanted to add, so one has to think a little bit about the scales which are involved in this business, right? So if you want to derive the Li-Wang-Yang formula, for example, right? The energy which matters, or the momenta which matters, are momenta which are associated with this healing length scale. So maybe I can have a small picture somewhere. Is there a time somewhere? It's over there. When it is? 12 minutes. 12 minutes. Okay, so we have a potential, right? In our scaling, the potential, the scattering length is -1 plus kappa. Okay? Then you look at bigger scales. So this is the healing length in this language is n to the minus kappa over 2. Okay? So it corresponds to momenta of the order n to the kappa over 2. Right? Now, if you want to get the energy only to this order, it is enough that you consider correlation up to this length scale here. So for momenta that are larger than n to the kappa over 2. Okay? If you want to go to the V order, you need something more. And this is this computation that I do here. You want the contribution of excitation to be smaller than the V energy. This requires P to be, well, this means that you can neglect P that are smaller than is n to the kappa over 2 minus beta over 4. So there is a new length scale here with n to the minus kappa over 2 plus beta over 4, where beta is this diluteness parameter which I wrote here. In the thermodynamic limit, maybe you are more used to that language. This one corresponds to rho to the minus 1/2. Okay? This guy here corresponds to rho to the minus 1/2 times rho to the minus 1/4. So it's a larger length scale. And you have to keep into account correlations up to this order here in order to get to the right energy. You cannot neglect what happens here as we did for the Li-Wang-Yang term. Okay, so that's about the length scale. So let's move on. So this is Wu ideas. Maybe it's the most important thing that I wanted to say. So Wu's idea is, okay, let's look at the expression that we have here. We have the Li-Wang-Yang, and then there is this thing here. So how do we compute the next order? We apply perturbation theory. right? If you do perturbation theory, keeping the Q as your unperturbed Hamiltonian and these C and V guys as the perturbation. If you do first order perturbation theory, right, the ground state of Q is just the vacuum. The expectation of these guys here in the vacuum is equal to 0, so you get 0 contribution. So you have to go to second order perturbation theory in order to get the next correction. And second order perturbation theory means that a good candidate for the trial state, for the ground state, is to take the unperturbed ground state, just a vacuum, and then you perturb with this, right, C star is the perturbation. This is the only perturbation which is not 0 in the vacuum, so we only have to keep track of this one. And then you take the inverse of the free Hamiltonian, so to say. And if you look in this business what it is, you find this expression here, which I wrote as vacuum plus A star times the vacuum. Okay? So this looks like, this is what perturbation theory suggests. It's a good ansatz for the trial state to get to the right energy. Okay. Now, if you do computation with this psi here, you will find that indeed, if you compute the expectation of this operator here, which is what we had in the previous page, the correction to the Lee-Wang-Yang energy, you get some terms, and if you compute these terms, these are exactly the Wu term in the expression that we had, in the formula that we had in the first or second slide. Okay, so maybe it doesn't make sense to do the full computation, but if you look here, A star, you have free creations operator. The C, you have free annihilation operator, right? You take the vacuum expectation, so you have to contract them. Okay, so at the end, you will end up with a sum which involves 2 factors of sigma, one from here and one from the C, and one denominator 1 over p squared. The sigma factors behave like 1 over momentum squared. And we have 2 sums, 2 momenta, right? It is 1 over momentum to the 6, summed over 2 momenta, and that's your logarithmic divergence. Okay, so that's how you create this logarithmic divergence looking at these terms here from this formula. Anyway, this gives you the right energy. So you may think when we are done, we just take psi as our trial state and we get to the right energy. But this does not work. And the reason it does not work is because the norm of this C is large. If kappa is larger than 4 over 7, you see this as a huge norm. And when you divide your psi by the norm, you are going to screw up the energy. Okay, so you have to somehow find a method to do perturbation theory, but without looking at the norm. And well, we tried to implement it with a unitary transformation, right? You take psi to be e to this antisymmetric operator, A star minus A. If you take psi like that, then it's easy to see when you expand the exponential in the usual Duhamel expansion, of course, you get a lot of commutators, right? Some of these commutators, the first commutator with the C's and the second commutator with the Q and the nu, and then the quartic term, they generate exactly the terms that we need to get the Wu terms. So we get the same terms that we had here. The terms we were happy about because they produce the correct Wu energy, right? So we see that they also come out if we take the unitary approach. And now we don't have a problem with the normalization, of course, because these guys are unitary operators, so the norm of psi is 1. Okay? So that's a good sign, but of course, in order to use these terms in the expansion, it means that you can control the expansion, you can control the convergence of expansion. Okay? So can we control the convergence of expansion? So this, I wrote down the expansion for a general observable O. So we have all the fully expanded terms, and then you have an error term that you have to control, right? From, oops. Here. So from some of these expanded terms, we get the contribution we want, so these 2 guys here. All the other fully expanded terms can be proven to be small. In fact, you can do it sort by power counting. You see that you can cut it off. The main question is how can we control the error term, okay? I mean, it's how we're going to control the error term. I mean, my co-authors also insist on the fact that it's not even clear whether this is well defined as a unitary operator, okay? Because it's A and the star are unbounded operators. So in principle, I wrote it like that. It is not completely clear that this makes sense, okay? So you can think of it in terms of making sense of expansion, or can you control the convergence of expansion, or both things together. Yeah. Yes. Is defined here. This is A star. This cubic operator in A star operator. is coming from perturbation theory. Okay, so turns out that in order to, well, show that this is well defined and to control the convergence of expansion, it's very useful to introduce a cutoff on the local number of particles. So here I'm defining an operator NL of x, which counts how many particles, but in fact I'm talking about excitations now because I removed everything else. So how many cubic excitation I have in a ball of radius L around the point x. Okay? So now how should we choose this length scale L? Well, if you remember, I told you that you can cut off this sigma function, which creates the quadratic excitation, at this momentum scale, how was it? N to the minus kappa over 2 plus beta over 4. So this means, it was the momentum of the opposite, but this means that this function here decays on these scales. Okay, it's going fast to 0. You want to use the fact that this decays very fast when you go beyond this scale here. In fact, you can improve a bit this scale here. You can go down to this scale here. The sigma, right, the cutoff acts on this scale here, but you have some decay also before the cutoff, which implies, if you do the computation, that the L2 norm of the sigma concentrates in balls of this radius here. And when I say that the L2 norm concentrates, it means that the sum of the localized 2 norms, so this is the 2 norm of the sigma localized in a small box with this size here. And the sum is comparable with the total number of the total norm of 2 norm of the sigma. Okay, so you already have some decay on this scale here, and therefore we choose the cutoff on this scale here. So we define a function, a cutoff theta, with a property that when you measure the local number of particles on ball of this radius, they are bounded by some small n to the epsilon. So n to the small exponent epsilon. Okay? And of course you can ask, isn't this going to affect the energy too much? Well, when you can compute what is the typical value of this local number of particles, you find it's n to the minus beta over 4, so it's much smaller than 1. So putting a cutoff on n to the epsilon, we don't expect it to change the energy too much. And in fact, we will show that the energy remains more or less the same, even if you introduce the cutoff. Okay, so the presence of the theta will not affect these fully expanded terms, which gives the Wu energy. But we hope that we can use it in order to prove a convergence of the expansion. So why can we use the cutoff to get the convergence of expansion? So I wanted to show you the main idea. So for simplicity, let me take instead of a new a tilde, which is more or less the same, but it's factorized in R and P. So if you remember before we had sigma P, and then we had something like that, but in the denominator we have R squared plus P squared plus R plus P squared. So now I simplified it a little bit, just to make the presentation simpler. But I wanted to show that with this A tilde, and using the cutoff, we can control the number of particles created by this operator here. This is the first thing that you want to do. If you want to control the convergence of expansion, you have these huge error terms, right? How do you handle the error terms? Well, maybe I can show it once again, 1 second. This is the error terms. And this psi is not the vacuum, there is still the transformation in it, right? So what you want to do, you want to take these commutators, but you want to bound it by some number of particles, for example, and then you want to know a priori that the number of particles or powers of the number of particles stay bounded. So the first thing that you have to understand is how can you bound the number of particles generated by this transformation? Well, you try to do Gronwall, right? So you put a parameter S, you do the derivative, you get the commutator between the generator A tilde and this number of particles. And if you work it out, you get this expression here. Now, when you see this expression, the first thing that you try to do is, well, let's just take the eta in L2 and the sigma in L2, they are here, right? And then I get a bunch of number of particles operator to control this AX, AY, AZ. And the total number of particles, you need n to the 3 halves, because we have n to the 3 halves here. You can decide to maybe balance it a little bit differently, but the total power here should be 3 halves. And then you see, the only thing I can do at this point, I can use this 1 over root n to get rid of one of this n calligraphic n to the 1 half. So I can go back to the original number of particles, but I get a huge constant in front. There is no way that you can prove a Gronwall estimate. I mean, you get a Gronwall estimate exponential growth in n. Okay, so this is very bad. Let's try to do it now using the cutoff theta, okay? And that's the next page, which is also the last page. So the same computation as before, the commutator, I got my two terms, right? But now I want to use the fact that the sigma and the eta decay on large scales. So I can restrict the integrals to these sets here, where now I have this length scale appearing, okay? So if I do now the x or the y and z integral, for example, right? With the cutoff, I just get rid of these operators, right? Because I know that the number of particles localized close to this point z or z minus u, doesn't matter what is the precise definition here. I know that this number of particles is bounded by n to the epsilon. So up to the price of paying this n to the epsilon correction here, I can get rid of these n factors, and at the end I only have n to the 1/2 instead of n to the 3/2 factors, which of course I can handle like that, and now I can do Gronwall, right? Because now I have a number of particles plus a correction, which is like that. So this, using the cutoff, we can improve the previous Gronwall, which was terrible, with exponential growth in n, to something like that, which is almost optimal up to this epsilon factor. Okay, so that's how you use the cutoff, and that's how you control the convergence of expansions, and that's how we prove our theorem. Thank you very much for your attention.